So now we're talking about relationships between pressure. What we're going to do is we're going to look at a sphere. Okay, and pretend that this sphere, this metal sphere, has a specific volume. We can change that volume magically without really opening the sphere up. Okay, kind of a sci-fi type of sphere. Okay, and what we're going to do is we're going to say that there's a certain amount of gas in here. So it's important to recognize that when we're dealing with this relationship, and this is Boyle's law, we've got to keep some things constant. So the things I'm going to keep constant here, right? Constants are going to be the amount of gas that's inside as well as the temperature. So I change temperature, things move faster. As they move faster, the pressure increases, right? The amount, same thing. If I don't put more material in there, it's going to have higher pressure because I have more stuff pushing on the inside, right? So if I think about amount, remember this is moles here. The temperature here, that's degrees Celsius or degrees Kelvin. Okay. And so we keep those constant, and what we're going to do is we're going to affect the changes here that I get with my container. All right. So what's going to happen here if I decrease the volume? Now, if I decrease volume, if I take a balloon, right? Imagine a balloon in my hand. If I've got a balloon, that balloon itself has a specific volume. It's got pressure on the inside, right? What happens if I take it and I squeeze one area? That area on the balloon is going to bulge, right? Or it's going to pop. Let's say I've got a perfect balloon and it doesn't pop. So you have one area of the balloon is going to bulge, so it sticks out one area. Okay. The reason being is that as I add pressure here, I'm forcing things to move to a different area. Now, if I had some friends, and I got some friends, and I put the balloon right here, sort of cradle it like a football, and squeeze down. Okay. Again, the balloon doesn't pop. But as I squeeze down, I'm beginning to feel more and more resistance here. And that resistance that I'm going to get from pushing down on that balloon, okay, is a response to me trying to contract the volume that's associated with this. So, as I do that, as I push pressure down, or excuse me, as I push the volume down, the pressure is going to go up. The same type of thing. If the volume goes up, and I don't change the amount of the temperature, right? What happens there? What's going to happen to pressure? Well, if you remember, we had a relationship here between force over area is equal to pressure, right? Now, if I take my magical sphere and I increase the inside, right? I'm increasing volume, yeah, but the amount of surface area that's in the inside of the sphere, as that increases, right? It means that the same amount of force is going to be applied here. So as this area increases, anytime you make the bottom of a fraction bigger, right, it makes the number smaller. So this pressure value is going to go down. Okay. So what these two things have is called an inverse relationship. Okay. All right. So there's an inverse relationship between those two. Now, Boyle noticed that there was this relationship between the two, and he came up with Boyle's law. All right. And Boyle's law, right, identified that volume, let's see over here, volume or pressure is equal to a constant times 1 over volume. Okay, so this constant that he's got is going to be related to as a B, and that's Boyle's constant. Okay, so these two guys have an inverse relationship. As pressure goes up, volume is going to go down, right? Makes sense. Good. So this inverse relationship is what I have up here, and that's called Boyle's law. Now let's go ahead and address a couple other laws that are associated with these things.